Welcome students to our video notes lesson on section 1.4 part 1, where the main theme of this video is going to be focused on one-sided limits. What they are, what their definition is, why they're important, and of course, how we can find them. Now, before we get into those limits though and finding them, it will help us to kind of review some unique functions that you may or may not have seen in your previous math classes leading up to now, but are handy in kind of examining one-sided limits, but also may be important for this section and also moving forward as we progress in calculus. The first one I want to revisit that you may or may not have seen in the past is called the greatest integer function. This is the function whose output, so it's important that we understand that the y value of this function, the value that comes out, is always an integer. Okay, it's always a whole number, and it's the greatest integer that was less than or equal to whatever the input was. So the input could be any kind of number. It can be a decimal, fraction, square root. It could be anything. So that's the number that can go inside, right? It's x, and that could be any kind of number, all real numbers. But the number that comes out, the y value, could only be an integer. And it's not just any integer. It's the greatest integer that's less than the number that went in. So for an example, if I were to plug in, say, 0.5, so that would be my x value, the y value that comes out would have to be the greatest integer that's less than 0.5. So it could not be 1 because 1 is greater than 0.5. It could not be -1 because -1 is not the greatest integer that's less than 0.5. It would have to be 0 because 0 is an integer and it's the greatest integer that's less than 0.5. In fact, if you look at the graph over here, you can see that for any decimal value between 0 and 1 along the x-axis, the corresponding y value is always going to be 0 because 0 is the greatest integer less than or equal to values of x that are between 0 and 1. But notice what happens right here at the x value of 1. There's an open circle on this value of 0 for y, and then a closed circle up here on the value of 1 for y. So when x, the input itself, is an integer, so let's say I were to plug 1 in there, remember the definition for y is the greatest integer that's either less than or equal to the input. So when the input, x, is an integer, the output is going to equal that value because the output has to be the greatest integer that's less than or equal to 1, or whatever the x value is. And in this case, if I plug in 1 for x, the greatest integer that's less than or equal to that would be 1. I can't use 0 because 0 is not the greatest integer that's less than or equal to 1. I couldn't use 2 because 2 is not less than or equal to 1. So it would have to be 1. And so you can see that's where the y values jump up from the last integer to the next integer. And then for any decimal value between 1 and 2, say 1.3 or something, if I were to plug that in as my input, because remember your input can be any kind of number, any real number, it's the output that has to be an integer. So whatever comes out, this number here would have to be an integer. It would have to be less than 1.3, but the greatest integer less than 1.3, which would be 1, right? 1 is an integer, and it's the greatest integer that's less than 1.3. So you can see that the y value, right, these are the outputs, are equal to 1 for any integer value of x between 1 and 2. But then once I get to 2, you can see the y value then becomes 2 and so on and so forth. So it creates these steps. You could say sometimes we also refer to this as the step function because it creates these step values along the y-axis or along the y values at all the integer marks, right? Because the y value can only be an integer, so it can't be any of these decimals in between 1 and 2 or between 2 and 3, etc. It can only be 0, 1, 2, 3, 4, etc. So anyways, we get these steps. So that's just kind of a quick review of that function. Then I also wanted to quickly remind you what the graphing transformations were for this function so that you could sort of quickly picture what the different variations of this function look like. So this one here, where it's just the brackets x, we call that the parent function, which kind of tells us what the simplest version of the function looks like, which is this. So notice the first step starts at 0, 0. Notice the step lengths are all 1 in length. So the length of the step is 1 unit long. Notice that the distance between steps is 1 unit tall. And let's see. Yeah, I think that's basically all we need to know about the parent function. So let's consider this version of the function. Some might refer to this as HK form or something like that. So we've got these 4 numerical values, right? These are the ways in which we can create sort of variations of this step function, is by introducing these numerical values. So notice that b is being multiplied to the x inside the bracket. A is being multiplied to the greatest integer because it's outside the bracket. And then h is being added or subtracted to the x inside the bracket. And then k is being added or subtracted from the greatest integer. So the b and the h values are going to change your x length or location, and then the a and k values will change your y height or location. So as a really quick reminder, the a value is going to change the distance between steps. So right now in the parent function, right, if we look back up here, this value is 1, right? The a value for the parent function is 1, which is why the distance between steps is 1. That's the a value there. So if a is something different, like 2, 3, or 1/2, 1/4, then that would determine the distance between the steps. That would change the distance between the steps. Now, if a happens to be negative, then the steps go down versus up. The b value, this is the one being multiplied to the x inside the bracket, would actually change the length of the step. But it doesn't do it directly. Like the a value is directly changing the distance between steps, but b changes the length of each step by a reciprocal. I'll show you in an example in a second. H, this is the number being subtracted from x inside the bracket. This is going to shift your steps left or right. And we have to also remember about h. I'm going to put a star by both b and h. Anything inside a function is going to sort of do the opposite. So b changes the length of each step by a reciprocal, and then h will shift your graph left or right, and then I'll just put a little star here. Just remember it's the opposite sign. So if you have a minus h here, then you're actually going to go right, and then if it's plus a number, it's actually going to go left. And then, I'm ran out of room here, but I'll kind of move it over here. The k value will shift your steps up or down, and it's very direct. So that's just kind of a quick reminder of how that works. And so I kind of want you guys to try this one. Here's an equation here, and it's a variation of a greatest integer function, and we know that because of the brackets. Right? These tell us it's the greatest integer function. It's just a variation of the parent function. So notice the a value is still 1 because that's the number outside the bracket. But now I have a b value of 2 because that's the number being multiplied to the x inside the bracket. And then this is where we have to be careful. So the h value is actually what you would have being added or subtracted from x after you factor out the b value. So you may or may not remember that from pre-calculus. But actually, this is 2 times the quantity x minus 5/2, 5 over 2. So your h value is actually 5/2, or 2.5. And then since nothing was being added outside, then the k value is 0. So I'm going to kind of get you started. So that means your first step, so yeah, I forgot to mention that here. Your first step in your parent function, which in this case started at 0, 0, so that basically was our hk value from the parent function, right? Because there was nothing being added to the x inside the bracket or to the greatest integer outside the bracket. So that means h and k are both 0 for the parent function, and that's where our first step sort of begins, is right at that point. So in this case, our first step is going to begin at 2.5, 0. So I'm going to have you guys pause your video here. Go ahead and sketch what you think the graph of this greatest integer function will look like. After you do that, I want you to try to determine at what values of x the limits would not exist, and then come back and check your answer. Okay, so I hope you have a graph that looks similar to this one. So what I want you to notice is that because the b was equal to 2, that means the step length was only 1/2, right? You take b, you do the reciprocal of b, and that is how long your step length will be. The starter step, the first one, began at hk, which was 2.5, 0. And the steps were going up because a was positive. And that's pretty much it. So you can see here, these are our steps. So notice that at every half point, we have a place where our limit would not exist, because at every one of these halves, so like at 2.5, 3, 3.5, 4, and so on, we have a place where the left side of the function would not be able to meet up with the right side, right? The left side and right side are not approaching the same thing. So the places where the limits would not exist, there's infinitely many of them. It's at all the values of x equal to n over 2, where n is any integer, right? So 1 over 2, 2 over 2, 3 over 2, 4 over 2, 5 over 2, etc. That will help us being able to quickly sort of determine where the breaks and steps are. Then that's how we can quickly determine where our limits are not going to exist for this type of function. Okay, the next type of function that is helpful to kind of review are these functions called piecewise functions. So piecewise functions are the ones that have notation that kind of looks like this, where you have sort of this one-sided bracket, and then you've got these multiple equations. You could think of those as sub-functions, right? These are parts of, or they make up this full piecewise function. But these sub-functions are only existing on certain intervals, right? So f of x is not always equal to 5 minus x. It's only equal to 5 minus x for values of x that are less than 2. For values of x that are greater than 2, we think of it as this function here, the quantity x minus 2 squared plus 3. So it's kind of like we're taking these sub-functions, piecing them together over these intervals to create one larger piecewise function. So it's helpful to kind of remember how this works. So let's take a look here. This part of the function, I can tell, is linear because the x is to the first power. I can tell it would have a y-intercept of 5 and a slope of -1. So I'm going to do that all the way up till where x is 2, right? And I can't really go any further than that, because once x is greater than 2, I'm graphing a different function. So it would be kind of like that on the left-hand side. And then on the right-hand side of 2, right here, I have this, looks like a quadratic equation, looks like it's an HK form, looks like my a value is 1, so the shape of it will be the same as the parent function, but my HK is 2, 3. So this will start at the same point where the other one ended, actually, 2, 3, and it would kind of make a parabola from there. And this circle is going to remain open because neither one of these intervals is including 2. None of them have the equal sign underneath. So actually the domain for this function, domain again is all the possible x's that you can plug in, would be all real numbers except x cannot be 2. But it's everything other than that. It's everything to the left of 2 and everything to the right of 2, just not 2. And this is just an example of a piecewise function. Now the third function I want to go over, which I believe this might be the first time you're seeing this, is a function of this form where you have the absolute value of x divided by x, or maybe the reciprocal of that, the value of x divided by the absolute value of x. This type of function is very unique because it creates 2 steps. You could think of it as 2 steps. The reason for that is if you were to sort of ignore, let's say we were going to ignore the absolute value for a sec, right? Let's say I were going to take that away, then I'm just looking at x over x, right? This number divided by itself. A number divided by itself is basically going to divide out to equal 1. So that's really what the y value wants to equal. It wants to be 1. But how does the absolute value affect the outcome and create 2 different outputs? Well, the absolute value of x, right, if you remember, is equal to, this is a piecewise function, it equals x if x is greater than or equal to 0, but it equals the opposite of x if x is less than 0. An example of this, if I were to take the absolute value of 2, well, this is my x value, right? And that's already positive. 2, the number inside is already positive, so then the output just equals x, right? Just equals the input. Y equals x. But if I were to plug in -2, so that's my input, right? My input is now less than 0. My output would have to be the opposite of that, right? The opposite of -2, which is just 2. So now y is equal to the opposite of x. So let's say I'm looking at this function here. This over here. So let's say I have f of -2, right? So in the numerator, I'm taking the opposite of -2, and then in the denominator, I just have -2, right? So in the numerator, I would have +2, and in the denominator, it would still be -2, because the denominator doesn't have the absolute value. It's just x. So I end up with the positive value divided by the negative same value. Well, these are going to cancel to equal -1. In general, if I were to plug in an x value that's less than 0, then the absolute value of that would become the opposite of x, right? According to the definition of absolute value, according to this piecewise definition, when the input is less than 0, then the absolute value equals the opposite of that input. So in this scenario here, if I'm plugging in a value of x that's less than 0, then this absolute value of that x would become the opposite of x. Meanwhile, the denominator is still x, so that's how we end up with -1. So that's the other step. This function is either going to equal 1 for x's that are greater than 0, because it would just be positive number divided by itself, or it will equal -1 when the inputs are less than 0. And we saw an example of that right here. When I plugged in -2 into this equation, the top became positive, but the bottom stayed the same, and when I divided them, I got -1. Now notice I'm not including 0 in either of these intervals, because what happens if I plug in 0 into this particular function is I would have the absolute value of 0 over 0, which is 0 over 0, which is indeterminate or undefined. So actually this function is undefined when x is 0. But here's basically what it looks like. It has one step, so for x's that are greater than 0, that's on this side, on the right side, the y values are always equal to 1, because you're just dividing numbers by itself. 1 over 1, 2 over 2, 3 over 3, 4 over 4, they just all equal 1. And there's an open circle at 0, 1. But for x is less than 0, the step is down here at -1, because now I'm dividing things like 2 divided by -2, 3 divided by -3, 4 divided by -4, etc. So the value of this function is always ever going to either be 1 or -1. So remember that, 1 or -1. So it's the function with 2 steps, one of them on the y value of 1, one of them on the y value of -1, and the place where the steps jump from the -1 to the +1 is at the value of x that causes the inside of the absolute value to be 0. Okay, so with that in mind, I want you to try to sketch the graph of this function, which notice is in a similar format. Look at your graph and determine at what values of x do the limits not exist. Go ahead, pause your video here and give it a try. Okay, so I'm hoping you had a similar graph. It has the 2 steps, right? One at the y value of +1, one at the y value of -1, and the break in steps happens when the inside of the absolute value is equal to 0, because that would be right when the inside of the absolute value is changing from positive to negative. So this one, the steps jump at the value of -2 on the x-axis. That's also the value of x where the limit wouldn't exist because now the left side is not equaling the right side. Okay, so now that we've taken a look at some unique functions, let's go ahead and jump into the first part of our vocabulary for section 1.4. So we're going to take a look at what a one-sided limit is. So now that we're looking at some of these kind of unique functions that have steps and jumps and things like that, we need to talk about the possibility of having a limit on just one side of a function. So that's what a one-sided limit is. It's the limit of a function as x approaches a real number from either the right or the left. Okay, so let's take a look at limit from the right. So this, by the way, is also referred to as a right-hand limit, and sometimes I'll abbreviate that as RHL. The RHL, or the limit from the right, is just what the limit, like what the function is approaching as x is approaching c, but from values greater than c. So we're just sort of looking at the right-hand side, and we're saying, okay, so I know that the right-hand side isn't approaching the same thing as the left, but I just want to know what the right-hand side is approaching. If I ignore the left and just look at the right, that's kind of what this is. And then limit from the left is the opposite, right? So sometimes we call it a left-handed limit. I will abbreviate this one as LHL, left-hand limit. And that's where we just look at what the function's approaching as x approaches c from values that are less than c. Okay, so let's take a look at this picture down here. So here's c, right? So we have this notation. We do this, the limit as x approaches c. And then if we put a little plus sign, like a little superscript, that means we're only looking at values of c on the right of c. So greater than c. So we're kind of having the function. So the function, in a sense, we're sort of following it. We're moving in the left direction. Because we're asking ourselves, and we're sort of ignoring everything else. We're just looking on the right side, and we're saying, okay, as the x values approach c from the right of c, so, you know, this looks like c plus 2, this looks like c plus 1 going down to c. As the x's do that, what are the corresponding y values getting closer to? Oh, it looks like they're getting closer to 1. So we could say that the right-hand limit for this function at c is 1. Okay, so then we kind of open up again and look at the rest of it. The left-hand limit at c, so now we're looking as x is approaching c on the left-hand side of c, so values of c that are, values that are less than c, values of x that are less than c. So we're kind of moving to the right, actually, but because we're on the left of c. And then we sort of ignore everything greater than c, we're only looking at less than c, and we just kind of say, okay, as the x values are approaching c on the right, on the left, excuse me, the values of x on the left as they're approaching c, then it looks like my y value wants to be at 2, right? The y values for the function are approaching 2. So we could say that the limit as x approaches c, and then we put a little minus sign. We put a little superscript of a minus sign, and that means I'm approaching c from the left, and the value of that limit would be 2. The function wants to approach 2 for values of x that are less than c. So we could say that the left-hand limit at c would be 2. So that's kind of what we mean by these right-hand limits. So the limit at c, right, limit as x approaches just c, that limit does not exist. Because we have learned in previous sections that the left-hand side and the right-hand side need to be coming together to touch, right? If we were to kind of follow it with our fingers, they would need to be coming together at the same point. The left side and the right side need to be approaching the same thing in order for the limit as x approaches c to exist. So this limit does not exist. But if I put a little plus, if I'm just looking at the right-hand side, then I could say, well, that limit is 1. If I put a little minus, so I'm just looking at the left-hand side, I could say, well, that limit is 2. So now we're kind of allowed to let limits exist on just one side or the other, and we indicate that with these little superscripts, plus and minus. Okay, so that brings us to this next theorem here, which is talking about the existence of a limit. So when we just say a limit and we don't say one-sided or from the right or the left, that implies a two-sided limit. Two-sided limit is the ones that we've been working with up until now, where you're just supposed to have the left-hand side equaling the right-hand side. So we're saying, okay, let f be a function. C would be an x value, right? The x values are approaching c. L would be a y value. So these are the values that the function would equal. So the limit of f of c, I should put f of x right here. The limit of f of x as x approaches c, right, that's my x value, is L, this would be the y value, if and only if the limit as x approaches c from the right would have to equal the limit as x approaches c from the left. So now we have this, we're kind of getting a little bit more specific. And both of those limits would have to equal that y value of L. So now that we've sort of learned about one-sided limits, now we know that whenever this superscript is missing, so whenever we just see this notation, the limit as x approaches c, and there's no superscript there, this is implied to be a two-sided limit. And this limit only exists if and only if the right side limit equals the left side limit. Those have to be the same value. Lastly, we're just going to finish up with some examples. So here we're given these graphs of these different functions, and we're given a c value for both of these. And we're asked to determine the limit as x approaches c from the right, the limit as x approaches c from the left, and then the two-sided limit if it exists. So in the first example here, I have c is 1, so that would be like right here. So the limit as x approaches c from the right, so that means I'm starting from values that are greater than 1 and approaching 1. So that's this side. Looks like looks like on the right-hand side it wants to approach the y value of -5. But it also looks like it's approaching the same thing on the left, right? So we could say that the limit as x approaches c from the left of the function also equals -5. So therefore, the limit as x approaches c, the two-sided limit exists and equals -5, since both the right hand and the left hand equal -5. Now for example B, we're looking over here at -1, the x value of -1. So we can see right away that the two-sided limit does not exist because the left side and the right side are not coming together. But now we're able to kind of distinguish between the two and say, well, the limit as x approaches c from the right, so that would be over here, values of x that are greater than -1, heading toward -1. So it looks like that limit wants to equal 1, right? The y values are at the value of 1 for values of x that are greater than -1 but approaching -1, right? So we ignore this because those aren't approaching -1. This part is. Okay, and then the left-hand limit, that's when we're approaching c from the left, so from values of c less than c, so we're approaching this way. Looks like the function on that side is approaching the y value of 0. So the right-hand limit is +1, the left-hand limit is 0, and the two-sided limit does not exist because the left hand does not equal the right-hand limit. Go ahead and pause your video here. Give these two examples a try. Come back and check your answer. Okay, so for part A in the example, the c value that we were looking at is 2, so right here. So on the right-hand side, hopefully you saw that it was approaching 6, the y values, and then on the left-hand side over here was approaching 4, and then of course, because the left did not equal the right, then that two-sided limit did not exist. Then for this example over here, the x value in question was -2, so along sort of this section. So as the function approaches that x value on the right, I can see that the y value wants to go to -8. Same thing as it approaches that value on the left, the y value wants to go to -8. So we could say that the two-sided limit exists because the left and right are both approaching the same y value of -8. Now you may be wondering, well then what's this point all about? That point, if you remember, is the, quote, algebra view, right? That's what you would get if you just plugged -2 into the function. The value of f at -2 is equal to 4. But the left-hand side and the right-hand side are actually down here by -8, wanting to go to -8, and then for some random reason, this function just happens to equal 4 at -2. Okay, so in example 2, we're not given the graph, right? We're just given the equation. So we want to kind of have an idea either of like what does the graph look like, or, you know, could I simplify this or find out points where this function doesn't exist, that kind of thing. Well, I hope you're recognizing this equation here. This is the function that has the 2 steps, right? Also, I noticed that when x minus 9 is 0, a couple things are happening. One, the inside of the absolute value is changing sign, right? So this would happen when x is 9. And also, the denominator is equal to 0. In fact, both numerator and the denominator would equal 0. So at x equals 9, I'd have 0 over 0, which doesn't exist. So that is where the steps are jumping. So here's the x value of 9. I would have one step at 1 on the right side, and then one step at -1 on the left. So looking at the way this limit is set up, we are trying to find the limit as x approaches 9 from the right. So that would mean we're over here, we're to the right of 9, right? X is approaching 9 from the right. The y value is equal to +1. So it's an easy limit to find if you kind of recognize this structure. Remember that it's the 2 steps and can kind of picture this graph. So anyway, there's that one. Now for this function here in part B, this is one where it's not so easy to try to picture the graph. So instead what I'm going to do is kind of consider what's happening at x equals -2 in this function, and then what's happening slightly to the right of -2. So if I plug -2 just in for x in this function, I'd have -2 being divided by -2 squared minus 4, or 4 minus 4. So I would end up with -2 over 0. So I know that at x equals -2, this function is undefined. In fact, if you can remember from pre-calc, I know there's a vertical asymptote at x equals -2. So then the question becomes, all right, so I know that this function is, you know, has a sort of an extreme situation here at x equals -2. But when I look at just the right-hand side, so this would be values that are greater than -2, for example, like -1.9 or -1.99, these kind of numbers, right? They'd be greater than -2. So if I were to plug those in, I'll just do -1.9. I'd have -1.9 squared minus 4. I don't know exactly what that is, but I know that altogether it would be a number that's less than 0, because -1.9, if I squared it, would actually be less than -2 if I squared that. Because when I square them, these numbers turn positive, and then this would be less than -2 squared. So I know that this number would be less than 4, and I'm subtracting 4, so I'd have a number inside a square root that's negative. Well, we know that that can't exist, right? Or at least not in the real numbers, right? We know that's not a real number, and so when we are working with these functions, we are working with functions where the domain would only be values of x that create real number values for y. So the outputs have to be real numbers, which this is not. Does not equal a real number. So actually, this limit doesn't exist on the right-hand side because the function itself is not equal to a real number for values of x that are approaching -2 from the right. So we would just say this limit does not exist for really reasons that more pertain to the domain, right? Because these values of x approaching -2 from the right actually would not be in the domain for this function. This function's domain, let's just take a look at that actually. So this function can only have real number outputs if the values of x are either greater than 2 or less than -2. These values of x, if I plugged them in here and squared them and subtracted 4, would create positive numbers under that square root, which would create real numbers for my outputs. So my domain has to be one of these two things, right? So I have to exclude any value of x between -2 and 2, which is what these would be if I'm approaching -2 from the right. Okay, how about you guys go ahead and try to find these limits down below. All right, so for the first one in part A, so these actually are kind of a review of finding limits from section 1.3, right? I used analytical methods here. This was a function where if I plugged in 3, if I figured out what this function was at 3, I had 0 over 0. So this was one of the functions where I had to multiply by the conjugate to rationalize the denominator. So I did that, and then when I multiplied these together, I got x minus 3 in the denominator, which canceled the x with the x minus 3 in the numerator. And then that left us with just the square root of x plus the square root of 3 over 1. And I'm taking the limit of that as x approaches 3 from the left, but it's still approaching 3. So I can just go ahead and substitute in the 3 now. And then I just have the square root of 3 plus the square root of 3, which is equal to 2 rad 3. So this limit is one where the left-hand side equals the right-hand side, and so this two-sided limit exists. So I can just kind of use the same methods I would use if I were finding a two-sided limit, since this two-sided limit exists. So the left side limit would also equal 2 times square root 3. Similar thing here in B. This is one where at first if I plug in 4, I get 4 minus 4 over 4 squared minus 16, that's 0 over 0. So this is one of the ones where you need to factor both numerator and denominator and then cancel common factors, which in this case was the x minus 4, which left me with negative 1 over x plus 4. And I'm taking the limit of that as x approaches 4 from the right. But again, this is one of those limits where the limit from the left would equal the limit from the right. So I can just plug 4 in at this point, right? Negative 1 over 4 plus 4 is just negative 1 over 8. And there's my limit. Last but not least, we're going to take a look at a couple piecewise functions. So we're going to find the limit of the following function if it exists, and if it does not, we're going to try to explain why. So in this first one, we have the limit as x approaches negative 1 of this function p of x. This is, again, a two-sided limit here because I don't see any like plus or minus superscript. So this is a two-sided limit. So I need to make sure that on the left side and the right side of negative 1, the function is approaching the same value. Now from the graph, I can see that it is not, right? I can see that there is a jump here at negative 1. So no, this limit does not exist because the limit as x approaches negative 1 from the right does not equal the limit as x approaches negative 1 from the left. That would be our reason. Now, let's suppose you didn't have the graph. Okay, so let's say we didn't have this and all we have is just this piecewise equation. What we could do is find the limit as x approaches negative 1 from the right. That's this one here. We could find the right-hand limit by looking at what the values of p of x equal when x is on the right-hand side, right? Right-hand side of negative 1 would be values that are greater than or equal to negative 1. So I could plug negative 1 in for x for that right-hand side piece. And I would have 1 minus 3 equals negative 2. So that's my right-hand limit. I could find my left-hand limit by looking at what the values of p of x equal for values of x that are less than negative 1. So I know I'm on the left. And I can see that that equals 1. And since 1 is not equal to negative 2, my right-hand limit does not equal my left-hand limit. Therefore, the limit at negative 1 does not exist. You go ahead and try this one. All right, so for this practice one, we can see that this was looking for a one-sided limit, specifically just what was happening as x approaches 1 from the right-hand side. So we're looking at values of x that are greater than 1 but approaching 1 from the right. I can see that my y values are heading up to the value of 2. Also, if I just were to not have the graph, right, and just kind of look at this piecewise equation, I could say, okay, this is the part where x is greater than 1. So this would be where my right-hand limit's happening. And I can just plug 1 in for x in that piece, and I notice I get 2. And that concludes our lesson for 1.4 Part 1. See you in class.